So I think it's a good time to start. We have already quite a number of people. So it's a great pleasure to have today for our talk Nati Linial from Hebrew University in Jerusalem. Right, again, Nati's biography you can read online. I will not go over various distinctions, and there are numerous which Nati got. And so he will talk about hypertrees. Please, Nati.
Thank you, Benny. It's a pleasure to be here. And feel free to ask questions either directly or by chat through Benny. The more interactive, the better it is. So this subject is, for me, part of a much bigger picture of what I call high-dimensional combinatorics. I will not elaborate on this, but you can find things on my webpage and so on. The idea is that the standard combinatorial objects that we investigate, if you think about them geometrically, they're one-dimensional, and most of them have very interesting higher dimensional analogs and lots of interesting things to investigate. And so you understand that hypertrees, which we will define and speak about at length, are the higher dimensional analogs of trees. Okay. So we need some terminology, and this is really crucial. Just make sure that you're with me on these basic definitions, because without them, it will be very difficult to follow. The definitions are very simple, but they're crucial for the talk. So the main thing that we define here is the notion of simplicial complex. So a simplicial complex has a set of vertices. Everything is going to be finite for us. And it's a collection of subsets of V, which is, this collection is closed down. So if A is in the family and B is a subset of A, then B is in the family as well. That's the most crucial thing to notice. And we have some more terminology. The members of the simplicial complex, we call them faces or simplices, and we associate a dimension with them. And the dimension of a set A is just its cardinality -1. If you think about it for a moment, it makes a lot of sense. We associate with the singleton dimension 0, with the pair of vertices dimension 1, and so on. So these things make a lot of sense. And the dimension of the whole simplicial complex is just the largest dimension of a face in X. Okay, so this is really crucial. It's not a complicated definition. We're going to be using it throughout. We're only going to talk about simplicial complexes in this lecture. So just to connect it to the comments that I made at the beginning, you see that a graph is, from this perspective, is the same thing as a one-dimensional simplicial complex. Why? It has two types of faces, zero-dimensional faces, which we normally call vertices, and one-dimensional faces that we call edges. Okay, so now the game begins. Everything that we know about graphs, at least it makes sense to try and ask these questions about simplicial complexes and see, is it just the same thing? Does the question even make sense? Do new phenomena arise? And we will see all examples of everything that I just said. So a tree, what should a tree be in the language of simplicial complexes? So one good principle to follow when you do studies like this is to work in analogy. You look at the realm that you understand, the world of graphs, in this case, the world of trees, and you ask yourself, do these notions even make sense in the higher dimension? So a tree, we all know, it's a graph that is connected and acyclic. So if we want to define these things, or the analogous things for simplicial complexes, we should ask ourselves, do we know how to say connected, and do we know how to say acyclic? And then if we have these two notions, then we've got ourselves at least a concept. And whether it's interesting, whether interesting things to say about this remains to be checked. But at least we can start. So a crucial ingredient in what I'm going to talk to you today starts from a paper of Gil Kalai 40 years ago in the Israel Journal of Math. The paper is called Enumeration of Q-acyclic simplicial complexes, and he really defined the notion of hypertrees, which we're going to discuss today. It's a beautiful paper. I will here and there return to mention it. By the way, this paper is, I mean, the whole area of simplicial complexes is usually investigated within the realms of topology. But you will not need to know any topology for today's lecture. However, if you do, then you'll be able to see and understand here things that perhaps I don't say explicitly. And this is really, there is a lot of potential in that direction, but I want to make the talk very accessible. So I'm not even talking about any notions from topology. In a way, I am, but I will not even call them the right names and so on and so forth. I'm going to stay completely within the language of combinatorics. Okay. So we remember we were talking about how do we define connected and how do we define acyclic. So a good place to start is the notion of an incidence matrix of a graph. An incidence matrix of a graph is a matrix. The rows correspond to the vertices of the graph. The columns correspond to the edges of the graph. It's a matrix of 0, +1, and -1, mostly zeros. And in the column corresponding to the edge ij, there's a +1 in row I and -1 in row j. You could ask, why didn't I go the opposite? It's not a directed graph. And you'll see, I have to make a choice, but which choice I made doesn't matter. Everything that we do will be completely independent of this choice, whether I did plus and minus or minus and plus. So in this matrix allows us to define the notions of, or to see if the graph is connected, and whether the graph is cyclic or not. Connectivity, from this perspective, is equivalent to the fact that the left kernel of this matrix is trivial. Why? Because, so I'm telling you here very simple things which are easy to verify. I will not do these things. By the way, I already know in advance that I probably have more material than I will be able to cover, but it's okay. We'll cover whatever we cover. So things like this I will not even prove. You can think about it for 5 minutes and prove it to yourself that the left kernel.
Left means, Nati, when you take this matrix and you multiply.
I multiply on the left. I combine rows. So coming back to the matrix, I multiply on the left. Okay. Right. So it's a vector on the left, which I multiply by A and I get 0. Okay. So this is.
You combine kind of rows which corresponds to the vertex.
Exactly. So, okay. So since you asked, I simply take a connected component and I sum up all the rows corresponding to that connected component, I get 0. Why do I get 0? Because there is a +1 and -1 in every column. They sum to 0. And then just think one more second about this and you'll understand the statement that left kernel of this matrix is just the linear span of the indicator vectors of the connected components of G. So it's one-dimensional if and only if the graph is connected. What about cycles? We also want to be able to say acyclic. So the cycle space of G is exactly the right kernel of this matrix. Why? This is if you take a cycle and perhaps you multiply by ±1 in order to make all the entries vanish. So this is exactly the cycle space. So in other words, the graph is acyclic if and only if its right kernel is trivial. It has no vectors in the right kernel. Okay, so we have translated these basic notions from graph theory to the language of elementary linear algebra, and that will be very useful for us. So here is a theorem that you often prove in a basic discrete math class. It's very simple, it's very basic, and it's also completely elementary. And it says that the following properties, if you're looking at a graph with n vertices and n-1 edges, the following properties are equivalent. The graph is connected, the graph is acyclic, and the graph is collapsible. So the first two we spoke about. Collapsibility, you presumably don't know what that means, but we will talk about this later on, so don't worry about this. And how do we prove this? The rank of this matrix, when you add columns to the matrix, then the rank can only go up. So if I add all possible columns, the complete graphs, then the rank is n-1. So the rank of this matrix is at most n-1. On the other hand, the only linear dependence among the rows is what I said before, that you sum all the rows and you get 0, which means it's an n by n-1 matrix. There is one dimensional left kernel, so the graph is connected even only if the left kernel is one dimensional or trivial. And so we proved that being connected is the same as having a trivial left kernel. And being acyclic means that it has no right kernel at all. It has 0 right kernel. So in a different way of saying this thing, equivalent to both 1 and 2, this is just very elementary linear algebra. We're talking about the case where the columns of the matrix, which are n-1 in number, are linearly independent. So coming back to the statement that I made before, the equivalence of 1 and 2 is just linear algebra. You just calculate the rank of this matrix and you see that it's n-1. So now I want to speak about the third item in this theorem, about collapsibility. So an elementary collapse in a graph is the operation where you remove a vertex of degree 1 and a single edge that contains it. So a graph is collapsible if by repeatedly doing this thing, you eliminate all the edges. And it's a very easy thing. Now I'm not proving, I'm just talking to you intuitively. You can see quite easily that the graph is collapsible even only if it's a forest, and therefore you see that this is equivalent. So let us spend another second of this and try to understand. So the point, why let me say why I'm telling you what I'm telling you. So we saw that the equivalence of 1 and 2 of being connected and being acyclic is essentially just linear algebra. On the other hand, the condition of collapsibility is combinatorial. So it's a little surprising, and we will get a better understanding of this later on, that we can capture something linear algebraic in terms of combinatorics. So we will see how that works. So let's understand now collapse and elementary collapse in terms of this matrix, of the incidence matrix of the graph. So how do you see that a vertex has degree 1? In the corresponding row, there is a unique ±1 and everything else is 0. And in this case, let's say the single 1 appears in row I and column E. What we do in the elementary collapse, how does this translate to the language of linear algebra? Erase row I and we erase column E. And collapsibility means that if you keep doing these things, then eventually you remain with a matrix, with an empty matrix with no columns at all. And you can see, therefore, that this collapsibility implies acyclicity because when you collapse, if there is any come back to this notion that the last one here, that the n-1 columns are linearly independent, and the point is, if I do something like this, if I have a single 1 in a row, then the corresponding column cannot participate in any linear dependence. There is nothing to zero out that single ±1. So if there is a linear dependence, it's not going to participate in it. So we might as well eliminate it and continue. Okay, so this shows that collapsibility implies acyclicity, and this goes the other way around. These are all very simple facts. And I'm coming back to the comment that I made before. Somehow we managed to prove an equivalence between a linear algebraic notion, the equivalence of being connectivity and being connected and being acyclic, to a purely combinatorial condition. And this is very interesting, and we'll come back to this. So what remains true, the argument that says that collapsibility implies acyclicity, that remains, and I'll explain momentarily, that remains true in higher dimension, but the reverse inequality is no longer true. Okay, So how do we start talking about higher dimensional analogs of this? So all we did so far was completely graph theory, but our motivation is to be able to extend these notions to higher dimensional simplicial complexes. So we have to start from, you remember there was the incidence matrix, and now we have to do something similar in higher dimensions. So all I do here is I go to 2 dimensions. Everything that is already, rich enough to indicate to you the subtleties, the difficulties, the richer picture, and so on and so forth. So in 2-dimensional simplicial complexes, let me just to wrap up with the initial slides. There we have 0-dimensional, these are points, 1-dimensional, which are edges, and 2-dimensional faces, which are triangles or triples. And what we do, the analog of the incidence matrix, is this matrix, which we call delta 2. So this name comes from topology, but as I said, we're not going to refer to topology in any direct way whatsoever. So the rows here are indexed by the 1-dimensional faces or edges, and the columns are indexed by the 2-dimensional faces or triangles. And if you have the triangle IJK, then there are, again, most of the matrix is zeros, but it has pluses and minus elements in it. And how does it go? If, let's say, I is less than j than less than k, then in ij I write +1, in ik I write -1, in jk I write +1, so alternately. There is, I'm hiding here something a little bit under the rug, which I don't want to get too much into. This has to do with orientation, but I'll see, I'm not telling you, there is something additional about orientation that ought to be discussed, but I'm skipping it for just to be able to get to other places in the talk. Okay, so we want to develop an analogous theory. So we have to start by asking, there are certain obvious questions which we have to ask ourselves. What is the rank of this matrix? Which, remember, in the graph, it was n-1. And the answer here is n-1 choose D, which is rather nice to see. If D equals 1, then we recover the notion that we had before, that in the graph case, the rank was n-1. Why? Why is the rank exactly n-1 choose D? The fact, so this is as often the case when I want to say that A equals B, I prove it by A less than or equal and A larger than or equal to B. And so here
you're talking about general D, right? Not
here I'm talking about general D. D equals 2 was just for illustration, but I could have done it for 2 and you've seen it, but it's for the same money. So there is really, I wrote this one, I wrote for general D. So the reason is, and this is really crucial, and again, I'm not going to show it to you. If you never saw this, then this is really worthwhile writing a proof for yourself. The proof is very simple. It's just very simple inner algebra, that when you multiply these 2 matrices one by the other, you get the 0 matrix. And let me just throw in one word about topology here. Again, I want to not go into the, but when you have, this is something that for topologists is like breathing air, and for other people perhaps it's less obvious, but when you multiply 2 matrices and you get the 0 matrix, then the row space of this one is all in the left kernel of this, and the column space of this one is only in the right kernel of this. And one could ask, but these are inclusions, are they equalities? And checking whether this inclusion between the spaces is an equality or not, this leads to very basic notions in topology, like homology groups and so on. But this is just saying hello to a friend. I'm not going to dwell on this. Okay, so this proves an upper bound on the rank. Now we want to show a lower bound on the rank. How will we show it? We will find this many linearly independent columns, okay? And this will give us the set of D faces of a D-dimensional. So we're going to see for the first time a D-dimensional hypertree. Okay, so what is a D-dimensional hypertree? It's a D-dimensional simplicial complex. It has a full D-1 dimensional skeleton. So all the faces of dimension D-1 and below are there. Think of a graph. So in a graph, all the vertices, I want to assume that all the vertices are there. The whole action is just in the graph, which edges are there. And in a simplicial complex, a d-dimensional simplicial complex, the whole action is just which d-dimensional faces appear and which not. So it has the right number, n-1 choose d-dimensional faces. And now we're talking, now we use the lesson that we took about connected and acyclic. We write the analogous statement here. It has a trivial left kernel and it has a zero right kernel. So we are just repeating what we learned in looking at the graph situation. And in a different way, again, almost repeating almost verbatim what we said before about graphs, the n-1 choose d columns span the columns of the full matrix, what would be the complete graphs in the previous, okay. So we want to see an example. You know, we're talking about something. I mean, can we see an example? You know, one of the good things about combinatorics is that things are very concrete. You can, you know, look at them. It's you know, to me it's a great blessing. Perhaps other people are happier with more abstract things. I like very concrete mathematics, and that's a good reason why I do combinatorics. So let's have an example. So what are the simplest trees that you can think of in graph theory? I would say the simplest is a star and perhaps a path. I don't know if we will get to talk about path in the hypertrees, hyperpath. I will have them at the end, but I don't know if we'll get there. But stars are really very simple. So what's a star in the world of graphs? It's a tree made up of all the edges that contain a given vertex, right? That's a star. And the definition here, let's say vertex n, and the definition here is the same thing. Or which d faces are we going to take? D face, again, remember, it's a set of size d plus 1. It's all the d faces which contain the vertex n. Okay. So now I want to show you that this is really, so this is really a hypertree. It meets the definition that we made. So something from topology has snuck in the boundary operator. That's the name of this matrix, del D. But again, you can just call it del D if you prefer not to think about topology. Of the full d-dimensional n-vertex complex, it's an n choose d by n choose d plus 1. Again, it's a good thing always to think, you know, what happens when d equals 1? That's the situation that we know very well. It's an n by n choose 2. So that's like the incidence matrix of a complete graph. So this would be the same thing with a matrix of 0, 1, and -1. And rows are indexed by d minus 1 faces, so sets of size d, and columns are by d-dimensional faces, sets of size d plus 1. And now we want to show that the complex that we just described, the star, which is comprised of all the faces of dimension d minus 1 and below, and of the d faces which contain the vertex n, I want to show you that this is really a hypertree, a d-dimensional tree. So the analysis here, just wondering, so I'll run through this very quickly. It's really a very straightforward argument. We somehow we partition the columns into those faces which contain D and those which do not. And it's really, you find there an identity matrix which comes from throwing away element n, and the rest are spanned by the others. It's really a very simple linear algebra proof, which I'm going to more or less skim over. It's really a very simple argument, which shows you that that this is really, this is the argument. I'll just run over it. It's really a very, I've told you, I've described to you a family of n-1 choose D, d-dimensional faces, and I claim that these columns are linearly independent. It's really just a simple exercise in linear algebra, and let me go through it because there are lots of other things which I want to tell you. Okay, so let's talk about collapsibility. So you remember in the one-dimensional case in the world of graphs, An elementary collapse is I take a vertex of degree 1, and I throw away that vertex and the single edge that contains it. Here, a vertex is just a face of degree 0, of dimension 0, and there is a unique one-dimensional face which contains it, and we do something very similar here. If we find some d-1 dimensional face that is contained in a unique d-1 dimensional face tau, which is contained in a unique d-dimensional face sigma, then the corresponding elementary collapse is to throw away both tau and sigma. And we say that X is decollapsible if by repeatedly doing such operation, we eliminate all the D faces. And the same linear algebra argument that I told you before, in this row that there is a unique non-zero element, so it cannot participate in any linear dependence of the columns, so you might as well eliminate that row and that column, nothing will change. And the conclusion is that being collapsible implies being acyclic. But the opposite is no longer true in higher dimensions. So this is one thing I would really love you to take home with you. So let's look at this. Now we are in dimension 2, okay? So in the picture that we see here, here I want, perhaps I was speeding previously, now I want to go a bit more slowly because that's a beautiful example that if you never saw this before, then this is one thing that you can certainly take away from this lecture. So N is 6. Now, the one thing that I point out to you in this picture is that this vertex and this vertex is the same vertex, okay? I just draw it like this for convenience. This is the 6-point triangulation of the projective plane. If you know what that means, if doesn't, then let's think about it just as a simplicial complex. So n-1 choose D in this case, n-1 is 6 minus 1 is 5, D is 2, so they're supposed to be 10 two-dimensional faces. And if you look at this picture, there are really 10 triangles here. And what do we know about this? First of all, this is clearly not collapsible. Why? What is an elementary collapse in 2 dimensions? It's an edge, it's a one-dimensional face that is contained in a unique 2-dimensional face. But there is none here. You cannot even start collapsing. Why? Because every edge here is covered by exactly 2 two-dimensional faces. For example, the edge 4, 5 is an edge is contained in a triangle 4, 5, 6 and in a triangle 2, 4, 5. Perhaps a bit less obvious, but also true, is that the edge 1, 2 is contained in the face 1, 2, 6, but also in the face 1, 2, 4. So this is clearly not collapsible, okay? So you cannot even get started with this process of collapsing, of an elementary collapse. There is no elementary collapse that you can do, but what does this teach us? It teaches us more things. In a one-dimensional case, we had this miracle that being a tree was captured both by linear algebra conditions and by a combinatorial condition. But here, and so you could ask when I said, I mean, no one asked, but I'll ask myself, when I say this is the rank, one should ask rank over which field. And really, in the one-dimensional case, it didn't matter. The answer was the same. Why? Because we also had the combinatorial condition. And combinatorics doesn't know about fields in general. It does, but only if you really insist. And here, the answer does depend on the unifying field. So, for example, in this example that I showed you before, it's a hypertree if we're working over the rationals. But it's not a hypertree if we work over F2. The very same picture shows you this last statement. Why? Because just as I said before, every edge is covered twice by 2 two-dimensional faces. So if you sum up the columns in this matrix, you get the 0. So there is a linear dependence. So even the question or whether it's a hypertree or not, now we should say which field we're working over. Okay, so in dimension 2 and above, collapsibility is stronger than being a hypertree. And in fact, there is a conjecture which goes back to the original paper of Kalai, which I mentioned before, the paper that really started, that made the basic definition in this area. He conjectured that the two notions are really very, very different. In other words, that almost none of the n-vertex d-dimensional F-hypertrees are collapsible. And this remains open. We've thought about this. We've experimented with it a lot on the computer. It seems very, very solid, but we still don't know how to prove it.
So it in particular implies we don't know how to compute the number of this, right? This
absolutely. We don't know. It's worse than that, Benny. We don't know how to. Well, we have some ideas or some bounds, but in general, the counting problem, and I'll get to it, is still very wide open. There is lots of very basic things. Well, we will get to this. I will only mention, again, I am not even going to define these notions, but there is because now we do have to talk about topology, which I wanted to avoid. There's a chain of conditions or properties, being non-invasive, being collapsible, being contractible, being z-acyclic, being q-acyclic. And it's reasonable that each of these implications is statistically huge. So every set or every property that implies the other, statistically, the smaller one happens with probability tending to zero. But before we spoke about just the ratio between these two guys, that this over this goes to zero, but in fact, it's reasonable to assume that this over this goes to zero, this over this goes to zero. We don't know any of these. So this is a question. So is it true that any relation here is something that goes to zero? We don't know. So good. So as I said, one of the nice things about combinatorics is that you can look at examples. So can we see more examples of non-collapsible hypertrees? So here is one, which is very pretty. And even here, there is still a lot to investigate. So I'm now going to show you a construction. So let n be a prime. And let's fix a subset of the field of n elements of cardinality d+1. So the complex, the simplicial complex that I want to define to you is called the sum complex. It's the sum complex corresponding to the set A, XA, okay? So as we see, if I want to construct a hypertree to you, then it has a full d-1 dimensional skeleton. It contains all the faces of dimensions strictly smaller than d, and I have to tell you which d-dimensional faces it has. So when is sigma a d-dimensional face? So there is this condition. You add up. So remember, our vertices are elements of a field. You add up all the elements which are vertices in the face sigma, and the sum of them, so we are in the field, we can add, has to be in the set A. Just to it's a little confusing, so just to be very, very concrete, let's say D is 2. So you select somehow 3 elements in the field, let's say alpha, beta, gamma, and a triple is a 2-dimensional face. If triple XYZ is a face, if and only if X plus Y plus Z is either alpha or beta or gamma. So the definition, I think, should be clear now. And here is what we know about this. So this is in joint work with Roy Meshulam and with Rosenthal. And this is what we proved about this. This complex is always a Q hypertree. So it's both claims are quite non-trivial. On the other hand, the condition for collapsibility, so collapsibility is the stricter condition, and this is if and only if the elements of A form an arithmetic progression. So in the example that I said before, if let's say beta is the average of alpha plus gamma, then and only then will it be collapsible. So the nice thing about this is that, at least it illustrates the spirit that being collapsible is a much stronger condition, much stronger than being a hypertree. So Benny asked before, and this is a very natural thing to ask, one of the obvious things that combinatorialists always ask, if you come up with a new concept or with a new object, how many such things are there? So there is Kalai's formula, which, like many other things in math, was proved many years before by someone less prominent than Kalai. And I hope you learned it, and it's something that we usually teach in a basic discrete math class. Then the number of trees with vertex set 1 to n is n to the n minus 2. So the main result in the paper of Kalai that we already mentioned is the following beautiful formula, which I'm not even going to parse for you, but you go over all d-dimensional hypertrees. You calculate this number, it's the size of the d-1 dimensional homology. Let's not worry about this. In the case of trees, this is one-dimensional face, this is just one. And the outcome is beautiful, is n to the n minus 2 choose d. So in the case of d equals 1, you recover the Kalai's formula because this is n to the n minus 2. Here, it's 1 for every t, so it's counting trees. And so what Benny asked me for is something that we have really very naturally asked ourselves. How many without, so here in the formula of Kalai, you weigh the trees. You don't just count them. You assign weight to them. And the obvious thing is to ask how many are they? And you can derive already some bounds from Kalai's formula, but they're quite far from each other. So in work with Yuval Peled, we improved these bounds quite significantly, but we still don't have a full answer to this question. So let me tell you a little bit.
Can
yes.
You just go back? So H, so I maybe missed something. So for every tree you take, what is this? The number of faces, right? So what?
No. Let me, okay. I wanted to this is something I intended to skip, but if you ask,
just in one word, right?
No. I can give you an answer that I can say, without assuming any knowledge in topology. You see, when you in a tree, in a hypertree, you have an n-1 choose d by n-1 choose d submatrix of the full matrix, and this is really the determinant of that matrix, submatrix. So okay, let me just stay with this.
So maybe just for people who know. So when we do proof, let's say, of matrix tree theorem, right? It's something like we're multiplying this kind of modified this incidence matrix. So it's something like that for d dimensions.
Exactly. So moreover, it's a good thing that you mentioned it, because essentially what Kalai did in his paper is to adapt one of the known proofs of, so you can prove this formula via, it's of course a special case of the matrix tree formula, and he adapted that proof, and that's how he derived this formula. So it's not the connection is definitely there, but it takes some work to do this. Okay, so I want to give you a sense of how Yuval Peled and I, how we improved the estimates for the number of trees. Okay, so there is a whole world in which I've been very involved, and I won't have time to tell you about this, which is fascinating and still a lot to do there. You see, one of the main chapters of modern graph theory is the theory of random graphs. This is a deep and powerful and beautiful area. So, and I remember at the beginning I said, the name of the game is take anything that you know or you would like to know about graphs and see if does it make sense? I mean, does it make sense to ask these questions about high-dimensional simplicial complexes? Are there new interesting phenomena and so on and so forth? And now we're going to run into one example where this is the case. But basically, yes, you can, it definitely makes sense to define random simplicial complexes. So there is a paper that I wrote with Meshulam, whom I mentioned before, where we do this thing, and this started, there is now other models and so on. It's really, again, a fascinating sub area of this field. There is a lot still remains to be done there. And my work with Yuval Peled is somehow in that spirit, but much more remains open here. So here is how we derived, Peled and I, how we derived better estimates for the number of d-dimensional hypertrees. So before I do this, it's very tempting the whole time. There are so many beautiful things that I rush by, and at least I should mention. You see, you can let's talk for a moment about graph theory and trees. You can sample a tree. You have vertices 1 to n, and you can sample a tree uniformly, and that's very interesting. And you can ask what are the typical properties and so on. Like you do in those areas where probability theory and combinatorics interact. Completely interesting. There have been books written about this already in the 60s. So it's really a valid, interesting, rich area of research. But there is another very interesting and natural process which gives you trees, namely, again, connected to what's called the evolution of random graphs. These things, of course, tie up together in lots of beautiful ways. You start with n vertices and no edges, and then you select a random edge and you throw it in. And you keep throwing in edges, but if the edge that you want to throw in now closes a cycle, then no, you don't accept it, you eliminate it. And then eventually you come up with a tree. That's also giving you, of course, every tree can be created this way, but this gives you a different distribution over trees. And this is a much, first of all, the distribution is very, very different from uniform. There are papers from recent years telling you this, but there is a lot interesting things to understand about this. And in a way, what we're doing here is the analogous thing to that. We do precisely the same thing that is described with trees. We start with a d-1 dimensional skeleton. We pick a random d-dimensional face, and if possible, we add it to sigma. What's possible? Previously, a new edge was ruled out if it closed the cycle, and we do the same thing. So closing a cycle means that I've created something in the right kernel. I've created something in the cycle space. And here I do the same thing. I add it only if it doesn't create anything in the cycle space. And we have a terminology for this. If it creates a cycle space, we say that this face is in the shade of the complex that we presently have. So just to repeat, we start with an empty complex. Each time we add a new face that is not in the shade, a random one, which is not in the shade of X. So that's the process. And so it's the same thing with graphs as I described to you before. It's all okay. Now let me tell you. Okay, so I already revealed my next slide, but before and then let me tell you again a piece of methodology that I'm very keen on. I myself and my students, we use computers a lot. Mathematicians often, look down at this. Why do you want to use a computer? And I'm a great fan of this, and I've been practicing this for years. Actually, this is perhaps unfair to say because the people who really practice it are my students. But at least I tell them that this is what they should do. And with experiments, you can really learn a lot. And the slides that I'm going to show you now really illustrate this principle very, very nicely. It's one of the great, for me personally, one of the great success stories of this methodology of using computers. So the students here at the Hebrew University are required to do a project. So I don't know how many, quite a good number of years ago, a student knocks on my door and asks, do you have a project for me? And I told him, okay, let's say he seemed like a sharp guy and nice and so on. I said, okay, good, give you a project. But just to make sure that he knows what he's doing and I can trust his programming, I first gave him something where I knew what the outcome was going to be. I gave him exactly the process of what Erdős and Renyi called the evolution of random graphs, which is just almost what I said before. You start with a graph with n vertices and no edges, and in each step, you add a random edge. So now we don't discard. Every edge that comes in, comes in. But I want to, so initially, so look at this graph. Initially, every vertex, no new edge is in the shade. The edges are just a matching. As you go on, you start creating cycles. And so more and more, the probability that the new edge is not in the shade goes up, or the probability in the shade, not in the shade, goes down. So again, let me just repeat. Perhaps I should say this again. So the process is, you start with something like, I think, 100 vertices in this case. Yeah, it doesn't say this, but it's 100 vertices. Each time you add a new edge at random, and you mark whether or not it closes a cycle that didn't exist before. So the probability that it doesn't, this is what this graph shows. So initially they don't, and with time they do more and more and more. And if you know anything about Erdős-Renyi graphs, then you can discover all sorts of beautiful things. There is the phase transition, where a giant component emerges at around step half n, so it's around 50. You can even see when the graph becomes connected, which happens after about n log n steps. This is beautiful. So I looked at this and I said, yes, this guy knows how to program. I can trust him. And then I gave him the exact same thing in dimension 2. And when he came with the results, I almost fell off my chair. So this is what he came with, which, if you're used to seeing graphs of functions, then the difference between the two is really striking. For a physicist, this is a phase transition of type 1, and this is a phase transition of type, I always confuse, perhaps I said 1 and 2 the opposite way. I always confuse between them. So you see, so what is the experiment here? It's the same thing in 2 dimensions. You start with n vertex. I think it's also 100 in this case, if I remember correctly. And each time and it's a complete graph, the full 1-dimensional skeleton. And you each time, at each step, you add a random face. And you ask, have I, with this last face that I added, have I created a new linear dependency? So you see that initially, the answer is no new. And then there is this very sharp phase transition. What does it mean, type 2 and type 1? Here, in this one, in the limit, the limit of this function has a discontinuous derivative at type n of time n over 2, or p equals 1 over n, but the function is continuous. With Yuval, in previous work, Yuval Peled, we analyzed this, and finally, after years, this graph, we managed to explain this. So here there is a short proof which I'll skip, explaining this. Okay, a little bit on how this worked, and this is about my work with Roy Meshulam on random graphs. And so a few words about the theory of random simplicial complexes. One of the big results in the founding papers on random graphs by Erdős and Renyi in the early 60s, they proved that the threshold for graph connectivity is ln n over n, which means if you are in G and P, so now every pair, you have n vertices, every pair is independently of the rest, you decide to connect them by an edge with probability P and no edge with probability 1 minus P. And what this says is that, I mean, what I'm saying now, we have more precise statements to make here, but I don't want to get into that. So if the probability is less than 1 minus epsilon times ln n over n, then with high probability, the graph that you obtain is disconnected, and when it's a little bigger, then with high probability, the graph is connected. And with Roy Meshulam, when we started defining the notion of random simplicial complexes, we found out that the threshold for connectivity in this model were, again, well, what do? We have a full d minus 1 dimensional skeleton, and we add faces independently and with probability P. If you think about it for a moment, when d equals 1, it's precisely the Erdős-Renyi model. The threshold for connectivity, so for having a trivial, a left kernel is precisely d ln n over n. Again, it's nice because at d equals 1, it recovers the Erdős-Renyi theorem. And so the meaning is just as before. If P is a little less, then the kernel, left kernel is non-trivial. Above it is trivial. And really, perhaps the most fascinating result or dramatic result of Erdős and Renyi is the phase transition in random graphs. And we hear what it says. So you start with n isolated vertices and add edges, one random edge, one at a time. Initially, every edge is isolated. Later, small and simple connected components start to appear. Small means the cardinality is only logarithmic, and simple means they're either a tree or perhaps a tree plus one edge, so unicyclic. And then it's around a step a half n, and over a very short period of time, a giant component emerges. Giant means that it has linear cardinality, and time n over 2 corresponds to probability 1 over n. And something else happens at that phase transition, that up to that point, there is a positive probability that the graph is acyclic, but at that time, the probability of being acyclic goes down from 1 to 0. So if it's a little bit above this, then the graph almost surely contains a cycle. And this is what Yuval and I were looking for. So here, in the high-dimensional case, you can speak about the dichotomy between collapsible, non-collapsible, and cyclic and acyclic. And so this is summing up several papers at once, together with my students, Lior Aronshtam and Yuval Peled. Also, Meshulam was once a student of mine, together with Tomasz Luczak. And it shows you that the thresholds for collapsibility and for having a cycle are different. That one is about log d over n, that one is about d over n. And so what Yuval and I proved, and with this I think I'm out of time, so with this I'll finish, is that at that probability C over n, where the graph almost, the complex almost surely acquires a cycle, the shadow becomes huge. Rather than a large connected component, a fine connected component, you get a huge shadow. And this is what these two graphs show. So this really shows you how the shadow all of a sudden explodes, and it explodes and is really proportional to n choose d plus 1. There's still many good stories to tell, but I think with this I'll stop. My time is up. And thank you very much for your attention.
Okay, so thank you, Nati. So thank you, Nati, for great talk. Right, lots of inspiring questions. So it looks like there's really lots of things one can do, starting with actually counting this simplicial trees, which sounds like a cool question. So I ask a lot of questions. So any questions for people who are following?
Nati, does it make sense to ask what, so for example, in dimension 2, does it make sense to ask what it means if the hypertree is hypertree over any field, over all fields? Does this imply more restrictions?
Definitely. We still, so we believe that these asymptotic results do not depend on the field, but it's just a belief. We don't know this. So it's a little bit like you have in matrix theory, right? That you have theorems that when the matrix is automatically it's realizable over all fields. I'm sure there will be more subtle things, but if I have to guess, then these asymptotic theorems are not accurate enough to distinguish between examples. Of course, we can find, but I suspect that these asymptotic questions are not subtle enough to capture differences between the different fields.
I see.
So more questions? Okay.
Sorry.
Yeah.
I'd like to ask whether it is simpler to consider the labeled trees or unlabeled trees.
Yeah, so I don't think that here it makes a big difference. You know, the point is we're still so far from exact answers that this distinction is negligible. You know, the ratio can be at most n factorial, and here, let me see, do I have? This is about path. So here, okay, let me go back. You'll see it when I speak about Kalai's formula. You remember the exponent there was yeah, the exponent there was n to the n minus 2 choose d. So you see that if d is bigger than 1, then n factorial is which we usually think of as very big, is nothing. You know, at some point it will be very nice to be able to answer this question, but our state of knowledge is still such that this issue of are the vertices labeled or not is still way beyond what we're able to do at the moment.
Okay, thanks.
So
yeah, it's a little strange. It's a little strange for a combinatorialist to be working in a regime where n factorial is considered, you know, dust, that small thing that we completely ignore, but that's what it is here.
So do you think there are really nice answers here at some kind of nice formula? So it's more like asymptotics to understand. I mean, like
it would be really nice to. You know, there should be a number, for example. We know, yeah. I think we haven't exhausted this at all. Yeah, you know, understanding. This is conceivable to me that we should be able to find out the base of the exponent for various dimensions. You see here. So it's not that everything is hopeless. In these theorems, for example, which I mentioned here, our work is so I'm of course doing here a lot of injustice because I'm packing here something like 5 quite serious papers, but I wanted to put it all on one slide. Here we actually know the numbers. This is asymptotics, but here you tell me D, I can tell you what this threshold is. What constant to put here over n, and what this threshold here, we know these things very accurately. And this is because This comes from the analysis of this random process. So I don't think that it's out of the question whether that answers at this, granularity would come also with the question of counting the trees, but we are not there yet.
Some more questions? So if not, then again, thank you, Natalie, for the beautiful talk. Right, we can stop the recording.